All right, we are still in chapter 12. We looked at vapor pressure and how the vapor pressure has to equal the atmospheric pressure before you get to boiling of the liquid. And we also then looked at, well, what would happen if you added something to the solution? And so now this whole chapter, or this whole little section here, is going to be about adding something and making a solution. So now instead of having a pure water, what happens if we add something to water, and how does that change the freezing point and the boiling point and the vapor pressure? These are colligative properties, and we'll look more into that as we get going here. So colligative property is a property that depends on, and here's the key word, amount of the solute that's dissolved. All right, so this could be salt, okay, like we were talking about. If you're making your mac and cheese, you might add some salt to the boiling water so that it would change how it would boil, the boiling point. It does not depend on what you add, okay, so these properties will change the vapor pressure, will change the boiling point, will change the freezing point, and it doesn't matter which one you have, but the amount of it that you do add. All right, so we're going to just compare a little bit here. If you have pure water, okay, so this table down here, we're comparing pure water to a solution of salt added to water, okay, so a sodium chloride solution. The vapor pressure, and this is at a specific temperature, all right, so the vapor pressure at a specific pressure, I think I said temperature, is 23.8 torr. I think this is 25 degrees Celsius there for that vapor pressure. Now, what happens though if you had salt to it? This will lower the vapor pressure, okay? So that makes it a little bit harder. The urge of it to evaporate has gone down a little bit. How about the boiling point and the freezing point? So we know that a normal solution, a pure water solution, will boil at 100 degrees Celsius and freeze at 0. Now look at what happens if you add sodium chloride. How does that affect the boiling point? It goes from 100 to 100.8, and the freezing point goes from 0 to -3. Now, we could get it to go even higher than 100.8 or lower than -3 degrees by adding more, okay? The amount of it is what it makes the difference here. So if we add more salt, you could get it even a little higher. So main thing here, when you have pure water, it has a certain boiling point. You add some solute to it, okay, dissolved solute, it will affect the boiling point and make it a little bit higher. We call that elevation, okay, so a boiling point elevation. So we have a normal freezing, normal boiling point, and now we've expanded those, okay? The freezing point's a little lower than what it normally would be, and the boiling point's a little bit higher. All right, before we get into talking about how to actually calculate that change, let's look at this question. How many moles of dissolved solute particles are present in each of the following beakers? I have two beakers here. One has 1 mole of sodium chloride, and the other one has 2 moles of sucrose, C12, H22, O11. You're adding sugar and you're adding a salt. You put them into solution. Which one has more moles of solute? You would say, what would you say? Okay, important things to think about. Here you go. One thing you need to think about is, well, what does it mean when a salt like sodium chloride gets dissolved? What happens to it? All right, you should be able to say that when you have NaCl solid and you put it into solution, okay, so this is water, now we have aqueous sodium chloride. Now, aqueous sodium chloride, being an ionic, will form Na plus and Cl minus. So 1 mole of NaCl solid actually forms 2 moles of solute particles. You can see we formed 1 mole of sodium ions and 1 mole of chloride ions. So 1 mole of NaCl, 2 moles of solute. All right, does the same thing happen though when you put in sucrose? All right, so this is a sugar. You can just look at the structure. You see it's an organic compound. It has a lot of carbons, hydrogens, and oxygen. It is not ionic. It is a molecular substance, okay? So there's covalent bonds going on here. And we do know that sugar will dissolve in solution. Okay, you can put sugar in water. You don't see any of the sugar crystals anymore, but you can taste it, and you know it tastes sweet. So you know the sugar is there. So what happens when you add this to water? You still have sucrose. C12H22O11. This time now it's aqueous. All right, so we can take 2 moles, okay, of sucrose. Since we have a 1-to-1 here, we haven't done anything, just changed its phase. We have 2 moles of sucrose, gives us 2 moles of solute particles. All right, so with an ionic, make sure you realize if it is a soluble one in solution, it will then dissociate and break apart. And that's what the term electrolyte is. I feel like we probably have used this before, and I know we'll talk about it again when we talk about acids and bases. But an electrolyte is something that dissociates in solution and produces ions. Now, we've talked about ionic compounds that do this already. Those would all be strong electrolytes. Acids and bases are also electrolytes. In the chapter 15, we'll be talking about the difference between a strong electrolyte and a weak. So this can be broken down into strong or weak electrolytes, and it has to do with how much of it dissociates. If everything, all of the ionic compound that you put into solution completely separates into ions, that would be considered a strong one. If some of it remains molecular and only some of it dissociates, that would be a weak. We'll get into that more later. But the difference then between an electrolyte and a non-electrolyte is that a non-electrolyte does not make any ions. All right, so non-electrolyte, that would be your sucrose. That does not make any ions. If you look at this reaction, or it's not really a reaction, if you just look at the phase change from a solid into the aqueous, you don't see any ions present. However, if you have sodium chloride solid, you put that in, all of a sudden now you have sodium ions and chloride ions. All right, so moving on then. Let's look at this, and now let's do some calculations here. All right, so this is now the equation to help you calculate the change in temperature for the freezing point or the change in temperature for the boiling point. Now again, it only matters on how much solute you have. It doesn't matter what actual solute you have, but how much of it. So you can see from this equation that the change in temperature freezing is equal to some K, and this is Kf, this is the freezing point constant. All right, and that will be dependent on what solvent you have, times the moles of the solute particles divided by the kilograms of solvent. It was really important for us to do that previous slide where we looked at, starting with 1 mole of sodium chloride, how many moles of solute we made from that, and starting with 2 moles of sucrose, how many moles of solute. So it doesn't want the total amount of solute, it wants the total number of the solute particles, okay? So you have to make sure you have total number of solute particles, and then all divided by kilograms of the solvent, okay? So if you're talking about a solution of water, the solvent would be water. All right, the change in temperature for the boiling point is just the same, except now you have Kb, which is the boiling point constant. So these would have to be given to you. And then you might need to solve for the moles of solute particles, and you might need to get the amount of solvent that you're given into kilograms. All right, let's look here then what happens. So here's an example, we're adding sodium chloride. All right, normal 25 degrees Celsius for sodium chloride here. When you add it, the vapor pressure is 23.76 millimeters of mercury. As soon as you add the salt, we have now decreased, okay, the vapor pressure. And if we now heat this, you have to heat it higher, or the actual, sorry, you don't have to heat it higher. When you heat this, now it's not going to boil until you get to a higher temperature. All right, so now you're going to get to 100, it's not going to be boiling yet. You have an additional amount, that change in temperature boiling. So this is, the temperature it boils at is now greater than 100. Okay, we've elevated it. Now, if you are chilling this, okay, you are now getting this cold solution. Before it will freeze, go from a liquid to a solid, you need to get it even colder than 0. If it didn't have any salt, it would freeze at 0. Now you're getting it even colder. We can then just make sure we understand, okay, so the new temperature boiling is equal to the normal boiling that's an I, plus the change in temperature boiling that you have just calculated. So calculate this right here. To find the new boiling point, you will then take the normal one and you will add that change in temperature boiling. All right, the new temperature freezing then would be equal to the normal freezing point. Now you're going to subtract the change in temperature freezing. All right, so this can be very helpful. I would probably try to tell your instructor or teacher that you probably need to test this out by making some ice cream, okay, by adding salt to water. It's one of those great experiments that everyone should try. Even if you don't do it in class, it's something you can easily do from home. You just need some cream, you need some sugar, and some vanilla usually, and you have that in an inner bag, and then in the outer bag you have ice and salt, okay? By adding some salt there, you're gonna get the cream and the sugar in your inside bag to freeze because you've gotten it to a lower temperature than the normal temperature of that ice. All right, so that's a great thing to try. Let's then actually do a calculation here. All right, so we're gonna try to do this calculation. A solution is prepared by dissolving 100 grams of calcium nitrate in 450 grams of water. What is the boiling point of the solution, given that the constant, this Kb for water, is 52 degrees Celsius times kilogram solvent per mole solute? Can we do it? So we are taking water, which we know normally would boil at 100 degrees Celsius. We are adding some calcium nitrate to it. Since we're adding a solute, we expect the boiling point to be higher than 100 degrees Celsius. We can figure out how much higher it's going to be by this equation right here. That change in temperature boiling is equal to the Kb, okay, which is going to be given to us right here, times the moles of the solute. Our solute that we have is calcium nitrate, divided by kilograms of the solvent. And the solvent here is going to be the water. All right, so we have to find moles of solute because it just gave me grams of the whole calcium nitrate. All right, so important thing to make sure you know is that calcium nitrate, you have your polyatomic ions memorized. We know that nitrate is NO3 minus. Calcium is Ca2 plus. So our correct formula would be CaNO3 2. Now this is a solid. We are going to put it in solution and it will dissociate. It is a strong electrolyte because it is an ionic compound. And what does it dissociate into? What ions do you form? Well, we would form calcium ions and we will form nitrate. Now look at the formula, it had NO3 2. That polyatomic ion stays together, but it doesn't say NO3 2, it's 2 nitrates. So it dissociates into the individual polyatomic ions. So that tells us that 1 mole of CaNO3 2 will form a total of how many moles of solute particles? Remember, in the balanced equation, that would be 1, so we can add up that 1 plus the 2, 3 moles solute particles. All right, so given that, we can get from grams of the whole thing to moles, and then once we get to moles, we can get to the moles of solute particles. So let's just set that up right here, 100.0 grams. Get into moles by finding the molar mass, add up calcium at 40, 2 nitrogens at 14 each, and total of 6 oxygens. I got 164 grams per mole for the molar mass. And then we can go from moles of the whole thing to moles of just solute particles, because we know when we put it into a solution, we will form 3 moles of solute particles for every 1 mole of the calcium nitrate. All right, you can check all your units are canceling. We canceled out grams of the calcium nitrate. Then we canceled out moles of calcium nitrate. We are left with moles of solute particles. And if you do the math right, it looks like I got 1.83. All right, then on the denominator, we have to get to kilograms of solvent. Our solvent was the 450 grams of water. You should be able to do this in your head at this point, but just to make sure we can all show it, take your 450 grams, and we know in 1 kilogram, you can have 1,000 grams. So this just moves the decimal place over 3 spots to the left. We have 0.450 kilograms of water. All right, we now have everything we need to find that change in temperature. Put the units all there. Let me switch. We're going to go here just so you can see this new thing working out. All right, so we can start with our constant. That was 0.52 degrees Celsius, kilograms solvent, all divided by moles of solute. And then all of this times the 1.83 moles of solute divided by 0.450 kilograms solvent. All right, do units cancel out? If you are trying to calculate a change in temperature, we would expect that to be in a unit of temperature, okay? So here we go, moles of solute on the bottom there, and on the top there they cancel. And kilograms of solvent is on the numerator up here, denominator down there. The only unit left is degrees Celsius. When I actually do the calculation, the change in temperature of the boiling point is 2.11 degrees Celsius. Now, make sure you realize that is the change in the temperature. So if you're asked for what is the new temperature or the elevated boiling point, you need to take the normal for water, that's 100 degrees Celsius, plus now that change, 2.11, and we get 102.11 degrees Celsius. All right, I think that should be pretty good. Let's go to the next slide. And here's just, I want to just make sure we have this concept figured out. If you have these 4 solutions here, we have pure water, we have a solution of 1 liter of water containing 3 moles of sucrose, 1 liter solution of water containing 2 moles of sodium chloride, and a 1 liter solution containing 1.5 moles of calcium phosphate. Would they all have the same freezing point, or which one has the lowest freezing point? So take a second, take a little pause here, and then come back with your answer. All right, I hope you have thought this through, and you should have been thinking about, well, what affects the change in temperature? So first off, we know pure water will have a, I said freezing point of 100. I was thinking boiling point there. Let's just fix that. For pure water, the freezing point is 0 degrees Celsius. It's good to make mistakes, right? As long as you figure out how to correct them. 0 degrees Celsius, okay? And we know that whenever you add a solute, okay, to the freezing point, you're going to lower it, okay? So we would elevate the boiling point, but the freezing point, we now decrease it. So it's going to freeze less than 0. So we know it's not going to be this one, because all the other ones now have something added to the water, so they would all be lower. Now, how much lower they go will depend on a couple factors. Okay, there's a constant, and that's going to be the same for all these cases since they're all water. The moles of solute particles, that is changing in all of these remaining three. The kilograms of solvent, since they're all the same volume, that's going to be the same. So the only thing that's going to matter here is how many moles of solute particles. The more moles of solute particles you have, the greater the change in temperature freezing, which would mean the lowest freezing point would be the one that has the greatest number of moles of solute particles. You then had to look at them. Sucrose, you would say, hey, that's not an electrolyte. It's a non-electrolyte. It does not make any ions. So if you have 3 moles of sucrose, you have 3 moles of particles. Now we'll have to compare that. Sodium chloride is NaCl. 2 moles of sodium chloride will end up giving you a total of 4 moles of particle because 1 sodium chloride gives 2 particles. And then looking at the formula for calcium phosphate, calcium's +2, phosphate's -3, so you have Ca3PO4 2. There's a total of 5 particles there. So 1 mole of calcium phosphate gives you 5 particles. So if you have 1.5 moles, you end up with 7.5 moles of particles. The greater the number of particles, the greater the change in temperature freezing. You take your normal freezing temperature, and then you're going to be subtracting. So this one would have the lowest temperature freezing. All right, I hope you're ready for the next lecture.